I'm super interested in that one because like I'm from the Python world, and like WASM and running things in Python in the browser is super interesting, and now we are hearing how to also run LLMs in the browser. That's going to be really super interesting talk. The stage is yours.
The stage is ours now. So let's do a selfie. Remember RISC-V, the first AI talk in FOSDEM. Say hello. Where's Peter? All right. So whatever. All right. Thank you very much. And today we're going to first through some crazy thing on RISC-V. And if you guys free, go to our RISC-V booth to take a look at all the crazy product we're making, and including a Romans 1 version, okay? So today I will go through a few brief on the RISC-V stage on the hardware side, and Peter will go into more deeper onto the software side. So then I will dash off to another talk on the VLC side about AI. So, and myself is Liang. I'm a software guy, make my money on the software guy. And then I founded deep computing during the COVID. And then, as I said, I'm very serious about software, and I start losing money in the hardware, probably same as Roman and 10 years. So, and then we make a lot of hardware for the past 3 years. So from 2023, we made the most expensive laptop, $5,000 laptops for 4 cores. So that marks the history. So it stay in the British Computer Museum in Milton Keynes. All right. So and then I do a 2024 8-core and the second generation laptop and the iPad with external modem, and David Patterson made the call to his wife using the tablet, and as an anonymous call, and his wife rejected it. So that is the story. So it runs Ubuntu and Fedora. So after that, I'm tired. I'm losing too much money in making our own laptop on the hardware. I decided I had to focus on making the motherboard for framework. And do come to frameworks booth and the RISC-V booth. You see how the motherboard works on the RISC-V and with the framework. So actually it's a repairable, replaceable, upgradable, multiple ISA architecture from ARM, x86, and RISC-V, and different RISC-V. And then, yeah, it's very good. And everything, all the designs are open source. You guys can make a module for the RISC framework and do whatever innovation you wanted to do. So this is the first generation that we used because it tested through the whole framework collaboration, and then use of the existing 4-core to make the motherboard, and then you launch it in a very low price. And then what happened now, we see in that the challenge of the RISC-V SoC is we don't know where to hit, what market is, and what compute powers, and what resource constraint, and we have time constraint as well. So for most of the startup. And since the ChatGPT, and then I think everybody is clear, whoever makes chipset, all in AI, nothing else better to do. So that is the trend. So and then we launch in 2025, we launch chiplet version of a motherboard, and then very good spec. You can run 14B model on the NPU SI, and very powerful. And that's the look like of the chip. And that's the motherboard before the DDR hits the supply chain. Now, if you want to get a 64 gig DDR, probably costs you $1,000. So that is the hype of AI. So in 2026, you will see our 16-core of RISC-V coming out with a customer AI instructions. So, and it's a 2-caster and support 32 gig LPDDR, it's 60 TOPS sparse and FP4, and it's pretty powerful and fun to play. And you will see a lot of customer feature like RVV and to different length. So that's our target of selling in March. So you guys can have a go on it and tell me what's wrong with it, okay? And all I say in that now, we RISC-V moved to AI, we find it out on Linux side, we don't have applications. No application at all, except GPT. right? So it's on the web browser. And that's I see. Video player doesn't use it, and Chrome doesn't use it. And until last year, end of last year, I managed to convince VLC, can you help me do a version of using all the local compute of the AI? So that's why my talk in the open media about video player. So the model is crazy, all different kind of models, right? And the AI framework is even more crazy, right? And a lot of porting and the framework, all the CPP stuff. And then I'm sure Roman Tanya knows about it, how painful it is on the whole rows. And all our hardware is porting. So we do a comparison on the Chrome side. It is very complex, right? It's Chromium is on RISC-V, but there's no Chrome at all. So, and Chromium is considered is not a safe version of browser because they don't have a security patch. So we're trying to crack Chromium and into talking to the local compute, and we'll see how it goes, right? That is Chromium's monopoly. So they have all the AI on the GPU side and the CPU side, but doesn't have anything for RISC-V at all, because RISC-V is so new that they have customer AI instructions, not just vectorized or SIMD. And Peter will talk about all the framework. He knows more than I do. I just finding out the problem, I have no solution for it. And that's the state of the AI side in the Chrome. So I was saying that Chrome is the biggest app on any the Linux platform for end user. So we will see the state of it, right? It's scary. So, and now probably I will pass it to Peter to explain more how he is going to fix all this for the local MPU, for the vectorized, for the customer instruction coming next year, all the chips. So, and he is going to explain a lot more than I do. Peter, pass on to you.
Thank you. So a little bit about myself. So I'm a W3C WebAssembly SIMD subgroup chair. I actually co-wrote some of the proposals that were standardized, like SIMD and LXSIMD. I'm currently championing the vector proposal as well. I'm a former web runtime engineer, so I worked a little bit on V8. I'm a checker core maintainer as well, if anybody even remembers what that is. So the picture sort of the previous slide made a reference to, so there's basically two ways to run inference in the browser. It's WebNN and WebAssembly. So, and for example, things like WebLLM would actually target one of the existing sort of ways, effectively. So if you look at WebNN, so there, usually the way this would work, there's underneath there is an ML runtime, and because we're talking about Linux laptops and maybe Android devices, that would be probably Linux or Android ML runtime. And the dispatcher part typically would sort of differentiate between what can run on CPU and what can run on NPU or some kind of accelerator. And the way it currently sort of expected to work is that sort of on Linux and Android you would have light RT, which is effectively a TensorFlow Lite. And the way then will go down lower is sort of on the CPU side you get excellent pack, which is what you would do to support your RB64 GCV with vectors enabled. And if you need to support something else, then you kind of basically start writing delegates. And so the accelerator side would be basically covered by existing matrix extension proposals. It's IME, AME, and VME. And depending on how they manage state, it might actually fall sort of like back to the XNN pack side, or it can actually be, might still have to implement as a delegate. So in NPUs, so the examples that Liang gave, the SVN and SpaceMate NPUs, they definitely have to be implemented as a delegate. And bigger devices like Tenstor and accelerator cards would also fall into this category. So we kind of, he left, so I can say that. So we kind of disagree a little bit in this sense because Liang sort of sees it as the ML runtime doesn't have to be light RT. So basically, there's two options. You either have to choose a different runtime and teach Chromium to integrate with it. And Chromium actually knows how to integrate with CoreML and Onyx runtime. Or you basically follow the passive least resistance and you work with creating a delegate for your NPU and so on and so forth. And I think so, state of RISC-V vector support in XNPAC is pretty good. At least, I mean, there might be still some operations missing, but generally it's made a pretty big progress. Then to the other side, so also part of the problem with the WebNN is that only Chromium supports WebNN, but not only Chromium supports WebAssembly. So, for example, Firefox would also would be able to use WebAssembly in Firefox. So the state of WebAssembly kind of looks like this. So when WebAssembly has a SIMD extension, and right now, sort of everything is relatively well until you kind of get to SIMD. So the scalar code lowers pretty good. WebAssembly has some quirks with floating point representation. That's actually handled really well because RISC-V has canonical lands, exactly the kind that WebAssembly wants. There's also a half-float proposal, which WebAssembly also would be able to lower to RISC-V native half-float. So it's a pretty good story, besides the SIMD. So WebAssembly SIMD is only 128-bit and it's fixed length. So that presents some actually fun challenges because realistically, for running something like TensorFlow, you would need to have vector operations. Without that, your performance basically is completely unacceptable. And if your registers are a lot bigger than 128, there's also implementations, RISC-V implementations, where taking less than full register of data doesn't actually increase your throughput. So basically, at that point, you might be decreasing the throughput of overall sort of execution. So the problem is actually not necessarily super unique to RISC-V because there are other instruction sets that either have larger than 128-bit SIMD, or they are flexible like SV, for example. So there is a proposal that would add vectors to WebAssembly. So it will be basically bytecode level vectors that can be sort of relatively well mapped to existing RVV instructions. So, and that's sort of, for the most part, is kind of the plan. So unfortunately, this is the state kind of the software stack and not necessarily a demo of how we fixed it yet. So hopefully next year we can come back and actually show that we fixed some of it or most of it. Probably not most of it, but at least some of it. So what sort of the next steps that can be sort of like taken in this? So obviously the Linux, sort of the ML runtime that will be integrated with the browser and support sort of further downstream from that runtime. Well, and sort of on the WebAssembly side, what's probably left to try is to actually implement the vector support. So for this, the proposal actually has been kind of lagging in sort of development for a while. But the next step would be basically to chain support and try to do a runtime prototype. V8 already supports RVV, but sort of like extending the support to use sort of the virtual vectors probably would be something to try. Yeah. Anyway, thank you. Questions?
We have 5 minutes for questions.
All right.
So can you talk about sort of relationship between WebNN and WebGPU? Because some communities actually prefer WebGPU, you know, to implement kind of the same functionality. So TinyGrad, for example, has WebGPU backend, and they're kind of happy about it.
So, yeah, so that's actually a good question. So the WebLLM does WebGPU as well as WebAssembly, for example. So, so WebNN generally it's a graph API, so you build a graph using WebNN and then basically execute that on a device accelerator. So WebGPU would definitely work for GPU-like devices, but not necessarily for the NPUs and the like, because basically it's a generic GPU interface, and so that's kind of the problem there, basically. So yeah. Any more questions?